Thank you. Thank you very much. And thanks very much to Stephen Harnett for inviting me. It's been a really great time for me. I've learned a huge amount. I have a new hope that phenomenality is something empirically accessible, and that's not something I really had before. And this is not a good sign. Speaking of phenomenality, this is not a phenomena I was hoping to have. Is there something going on? Oh, did my laptop go down? Or? Oh, no. What's that? Oh, I think my laptop just went asleep. There we go. That was it. Sorry. All right. Let's see. Some acknowledgements. I'm really fortunate to have a large team of scientists that I work with from very divergent backgrounds, like Nilesh Patankar. He's a computational fluid dynamicist. Todd Murphy is a control mathematician who works on a lot of cool math regarding control of high degree of freedom systems. And George Lauder, who is an evolutionary biologist. I think the thing that unites this very divergent group of investigators is their abject terror that I'm going to use this careful science that we've built together toward some flaky ideas about consciousness that I might have. I'm going to give you a quick roadmap of where we're going in the next 40 minutes. There's a lot of stuff to cover. I'm going to give you an introduction to an unusual non-visual animal, tell you about its prey capture behavior, how and where these fish sense, and where and how they move, and show you some amusing robotic implementations. And I'll argue that the resulting quantification of sensory and movement capability suggests that vision in water is poor and reduces the number of behavioral options that aquatic animals have, and that control engineering can help quantify why vision on land was the jet fuel for needing to cope with multiple behavioral options. Some paleobiological evidence from pre-terrestriality fossils, Perry, I should say, and how all of this relates to one type of consciousness, how we might span evolved gaps in this consciousness with things like eco-feedback technologies. So here's the animal, my favorite creature. It's a model system in neuroethology, the weakly electric fish. Here it is slowed down by 17 times. And it propagates traveling waves from head to tail to move forward. And now we're going to see it flip and moon us. This is the butt of the animal, believe it or not. And now it's going to start sending a traveling wave in the opposite direction. So like a car, it has a forward and a reverse gear, which is kind of remarkable. Here's its geometrically complex habitat in the Amazon. It's the flooded forests of the Amazon basin rivers and the rivers themselves. And both of those pictures are misleading in some sense because this is actually its environment. These are completely nocturnal animals. They hunt at night. And in fact, the water they hunt in is so murky that you put your hand in and it disappears anyway. So vision would be useless even if you were diurnal. So a really important part of the fish and pony show that we always give visitors to the lab is this. Here is a cheapo, Radio Shack powered speakers, and I'm going to dip some leads into the tank. And that's its electric field that's been transduced into sound, so we can conveniently hear it. All of these animals are emitting constantly this buzz of electrical energy. There's an amazing electric civilization going on in the rivers of the Amazon, where electric predators detect other electric fish by their emitted signals and hunt them. And it's a whole little evolutionary arms race, and I don't have time to talk about that, but it's kind of a fascinating thing, and this is the thing by which they perceive their environment. So a bit about their prey capture behavior. So this is some behavior I recorded now a decade ago We're in an infrared tank, infrared illuminated tank. I'm going to put a dot where there's a water flea, which is about 1.5 millimeters long. That's one of its preferred prey in its natural environment. And you'll see what it does. It goes by very quickly, so I'll show it to you twice. But there's the prey. And you notice that rapid reverse strike. So it's using its reverse gear in a very adept way. Here it is again. Forward, reverse, and capture. So this is an animal that is cephalized and in many ways similar to us, but nonetheless not necessarily forwardly oriented, which I think is also kind of a neat aspect of being a non-visual animal. This is an interface, just a snapshot of an interface I developed long ago for doing 3D motion capture of these animals' behavior. You set a bunch of things and do some projective geometry, and you're able to exactly reconstruct the kinematics of the animal's behavior. And so here's one of those reconstructions. All right, so now we know something I haven't yet mentioned is that there's 17,000 sensory receptors on the surfaces of its body scattered across the entire surface whose signals, whose activity is being modulated by this prey, and that line is just a line of closest approach. And so we really need to track the entire body surface, just as if you're doing studies of the retina, you'd want to track the position of the retina as somebody scanned a scene. So with that, we can look at how where these fish can sense and where and how they move. So this is a slice of a 3D simulation from the lab. A phylogenetic precursor of the spherical cow is a cylindrical fish, and that's shown here. So this animal, or this robot, or simulation, I should say, has only 2 sensors rather than 17,000. I've modified the voltage. I've boosted it by 400 times so that we can actually see the perturbation as this giant, non-ethologically relevant stimulus goes by. It's a plastic sphere that's 6 centimeters in diameter. So this is just done so I can sort of explain what's going on with this animal's sensory system. Right here we have sensor 1 minus sensor 2 as a function of time. And so you see a little dot that goes along the plot as a function of time, and you'll see the peak modulation is only 1 millivolt, which should be compared to that 4 volts. So the ball will go away. It's going to scan across, and I want you to watch what sort of happens to these equipotential lines, these red equipotential lines, isopotential lines, as that object goes by. All right, so what's going on here is that there's a very hard-to-see black line here, which indicates 2 volts, which is very slightly shifted to the left. And as a result, this sensor is very slightly larger, 1 millivolt larger, than this sensor whose equipotential line at 2 volts has not really modulated. So this is basically exactly the way in which this animal is perceiving its environment, except now imagine a 10 millivolt signal source and a 1 millimeter in size prey, and you see the signal processing challenges that this animal faces, which are really quite tremendous. All right, so I've done for many years now, this is a snapshot of over a decade ago of a very high fidelity simulation of the entire sensory system of this animal coupled to motion capture data. And here's a snapshot from one of those. Let me step you through very quickly about 8 years of modeling and experimental work on one slide. Here's an electric image model that tells us how to compute the signal on the skin of the animal as a function of the position of the prey. These are all empirically tested and validated models. Here's a sensor layout. As I said, I think I said 17,000. I'm sorry, that's actually 14,000 sensors. And it has lots of regional specializations. This is what we call the electrosensory fovea up in the head region here. We have an electric field model. We have a prey model. We have a model of, we have the movement of the animal, or we have a behavior model depending on what context we're using the simulations. We compute voltage histories on all 14,000 sensors, and then we use really accurate neural models, also empirically tested, to derive how the spike firing rates of the afferents are changing as a function of these prey. And that allows us to then ask, when could the animal detect the prey? And I'll show you the results of that. This requires an immense amount of computation, which we do using clusters. So here's a reconstruction of this, just the voltages now on the surface of the skin as a function of time. I'm not giving you the afferents. The modulation is about 0.1 to 1 microvolt due to the prey at the time of detection. So just to test our understanding, and also out of some actual interest in the technology itself, we've built a device that mimics this form of processing, which is actually new to robotics, and a bunch of companies are now very interested in using this technique. But essentially this is one algorithm I'll show you of many, but essentially the way it works is as that ball was approaching the skin, you could see these isopotential lines bunch up a little bit, and that is what we call a hot spot. If we unwrap the surface of the cylinder and just look at the gradient of the voltage on the surface of the cylinder, we can see a clear hot spot. And that gives us a very easy algorithm that we can do for behavior, which is find the hot spot, and if we want to avoid, move along a normal to where the hot spot is. If we want to attract, if we want to go toward, we flip the sign and we move toward. So let's see how that works. So this is completely autonomous. It's sending signals to a robotic gantry to move itself around. So it does quite nicely. And a more impressive demonstration is this, where all we've told it to do is go from one end of the tank to the next. And it's able to navigate through clutter with quite a lot of agility. There's really no competing technology out there in the underwater sensor space in terms of handling clutter like this. So we're pretty excited about how well it's worked. All right, so that was the how, but where do they sense? This is a really key question for us, and you'll see why. So what we're going to do is do those computations again, but we're going to shoot Daphne at the fish from 1,000 different directions and see at what point can the nervous system detect the presence of the prey. This is done using a pretty complex model, but all the parameters of the model were previously published. We didn't fit or tune any of the parameters of the model. And here's the result. The black dots are empirically measured prey detections, and the large solid shows us an isosurface as to where we predict this animal should be able to detect prey from the first point it can detect prey is on that surface of the shell. We don't have any points down here from the behavior because every time we fed this animal prey, it would capture it before the Daphnia got down below the animal. But we're pretty confident that this is actually the shape of what their sensory volume is. So how and where do they move? Well, we've done a whole lot of supercomputer simulations to figure out the force generation capabilities of these fins. One of the things we've seen is that not only is there thrust generated lengthwise with the fin, as you would expect, there's also a vertical force. And the angle of the vertical force to the longitudinal force is 10 degrees. And if we look at all the Amazonian electric fishes, this is 4 of 200 species or 5 of 200 species. They, in fact, have that 10-degree angle, which is pretty exciting to us in terms of verifying our models. We've also built a robot. Here's a quarter for a sense of scale, where we can play back the measured trajectories of the ribbon fin to start cracking some of their biomechanical secrets. And we've published some papers recently on some really nifty tricks that these fish can do that I don't really have time to tell you about. So now we're going to shift to quantifying the sensory and movement capabilities, so putting these two capabilities together, and argue that vision in water is poor, and this reduces behavioral options. So what is the fish's motor space? Well, let me give you an analogy for what a motor space is. And this is from control theory. This is from work done by Dubbins in 1957 and Reeds and Shep more recently. And the question is, if you have a mechanical system, how can you predict where it can get to given any feasible control input over a given delta t, over a given time interval? And so for a car that has forward and reverse, you could sort of imagine it can sort of go forward and reverse, and laterally is a little trickier, and as you increase delta t, these spaces round out because you can do parallel parking maneuvers and that sort of thing. So over time, this is where you get to, and that would be then the motor volume, if you will, for a car. All right, so I'm going to try to derive this for the fish. So what we do is we go back to our motion capture data, which essentially gives us 8 different parameters for each time step of the behavior. The time step is 17 milliseconds. And suppose we want a motor volume at 100 milliseconds. Well, so what we do is we look at where it is at one point and then where it is 100 milliseconds later, and we basically do some coordinate normalizations and collect point clouds like so. So here's a fish. Suppose it just moved there in 100 milliseconds. We take the point cloud of the body model, and we put it with reference to where it was at the beginning of that movement. And then we slide down to the next 100 millisecond bin, and we do the same thing. Suppose it went up that time, and then we just take that point cloud and refer it back to the original position. And so you can imagine you can get a whole bunch of these points this way, and then you can threshold an isosurface to get us the biomechanical capacity under at least prey capture behavior for this animal. And so here's what this looks like. So what I'm showing you here is in blue the sensory volume for prey, and in green where it can get to over a given delta t. This is a really important time point here, this 117 milliseconds, because it's approximately the delay time from sensory inflow to the animal to motor outflow. And we all have these kinds of latencies. For us, it's bigger. For this animal, it's 117 milliseconds. But what this delineates then is sort of what you might call the sensory motor event horizon, because anything that happens in that 117 milliseconds, the animal has basically no opportunity to sense and respond to. It's right at that threshold. All right. And so we can look at bigger ones, the motor volume for 366, and then one for later. So what happens when we add the sensing story to that picture is, again, imagine that this is your motor volume in a real car, and you're moving forward, and you've got headlights on in a fog, so it's a really short range. And imagine that this is, in fact, your sensory, you're going to move through that space in your sensory motor delay time. Well, one thing that's certain as death and taxes, is that anything that's in that space that you suddenly perceive, be it a deer or what have you, you'll collide with. There's absolutely no question of that. So this is something about, the limits of behavioral sort of competence given certain balances between biomechanical and sensory capacity. So let's get at that with the fish. Here it is again, the motor volume for 117 milliseconds and the sensory volume for prey. Surprising, these spaces are not much different in relative size for visual aquatic animals. When I first saw this data, I thought, okay, well that kind of makes sense because the animal's paying a metabolic cost for this sensing field. It's paying energy for its electric field. And to double the range of that field, it needs 16 times more energy, which gets to be more than they actually consume in their whole day. So it's going to be strong evolutionary constraints pushing down the size of that sensory volume. So I was really perturbed when I saw that a visual animal, the stone Morocco, hunts Daphnia, and this is its sensory volume that was documented by a different researcher. And if you imagine, like, these fish are sort of going several body lengths per second typically, it's going to also be in this highly, highly reactive sort of mode where it needs to respond immediately to any prey that would appear in its sensory envelope. And so there's something about then that it would need fairly simple direct transformations between sensory data and motor outflow. And so one can imagine then a taxonomy of these relationships where you sort of say there's a collision mode that animals can be in, and that happens when their stopping motor volume is larger than their sensory volume. Then there's a reactive mode, and that happens when these spaces are roughly equivalent. So your sensory space is roughly what space you'll use up in your sensory motor delay time, give or take a small number of multiples. And then deliberative mode, which is an entirely different animal, if you will, where you've got, and this is what we're kind of used to phenomenologically, where you've got this giant sensory space and this piddly stopping motor volume, which is given to us by biomechanics. And so what's going on here, and how did we get to here, to the deliberative mode? And I think the story actually comes back to these animals that were transitional between water and land. And this is Tiktaalik, one of those transitional animals. What happens, it turns out, when you pop an eyeball from the water to above water is that you go from attenuation lengths of 10 meters or so, and that's where over 60% of the signal is absorbed by the medium. So it's really like a fog compared to what we see on land. You go from 10-meter attenuation length to over 100 kilometers once you just move a few millimeters above the water surface. And so you go from, with only a small, fairly easy tweak of the corneal shape, to seeing only a few body lengths ahead of you, to being able to see this massive distance ahead of you. And I think this might have something to do with a certain form of awareness, as I'll say shortly. So to schematize, then, here's sensory and motor spaces kind of overlapping, and a predator is going through a fluid, bumps up to a prey, and has to reactively strike at it. And here's a situation of that predator having emerged onto land. The initial ones, presumably the amphibians, like Acanthostega, probably were still stuck in this mode but now they saw something way far away, and they would have been driven to do like a straight line path to this prey. But with a little bit of neural circuitry, and if I have time, I'll speculate on what that neural circuitry tweak might have been, then it could offload sort of some some possible trajectories into working memory. So put possible futures A, B, and C in working memory and select the max of likely fitness of those three trajectories. And that animal would have a giant advantage over perhaps the early amphibians that had to do straight line trajectories to things because they were still in this reactive mode, is the hypothesis. So I want to give you a thought or an intuition pump as to how control engineering can help us quantify why vision on land was the jet fuel for needing to cope with multiple behavioral options. And it's a really simple model, all right? So increased vision range increases time horizons, and increasing time horizons can lead to critical points where multiple local minima exist and deliberation over multiple futures becomes relevant. All right, so here's a ball. The equations of motion of a ball in a gravitational field are x double dot equals a gravitational acceleration. So so that will just be that. Now suppose we want to control this ball so that it doesn't fall to the ground. We just want to keep it up in space, all right? So we need to add a force. We're going to add this applied force of u over m. That will give us the right units for acceleration. So with applied force, for small time horizons, the optimal control is u equals mg. So that's just going to counteract gravity. It's like putting your hand under the ball and applying a force u equals mg. All right. So that's the optimal course for small time horizons. That's the optimal control. And what do I mean by optimal? I simply mean the control effort needed, the forces needed to control that ball. But what happens when you increase the time horizon and assume elastic impacts is that no longer becomes the optimal control with increased time horizon. And it's very simple. All you need to do is drop the ball and let gravity do its thing, and it comes up to almost the same place. You might have to apply a tiny little bit of additional force. But for the entire time that this thing was falling and bouncing up, you're not doing any force application. And so from an optimal control standpoint, that's a far better strategy. But that's a strategy that only emerges with increased time horizons. And so we're working on an elaboration of this argument to suggest that with increased distance, you don't just get a sort of a difference in degree, that you actually get a difference in kind once you have additional space to work over. That is the gift of vision on land. So some paleobiological evidence from pre-terrestrial fossils. As I thought about what could be any evidence for this kind of theory, one thing that occurred to me is that as you're driving in a fog, if you increase your headlight brightness, you don't get any additional benefit, right? And so the analog to that in water is if you increase your eye size, you can do better photon capture, and that becomes important for deep sea animals. But in terms of imaging, increasing eye size has diminishing returns. And so what the suggestion would then be is that in water you would see sort of a flatlining of the allometry of eye size with body size, and then upon emergence onto land you should see a big uptick. And so I'm working on this. I've sort of been talking to Jenny Clack and Neil Shubin about looking at the fossils they've discovered around terrestriality to see if this is true. And I've already done a little bit of initial looking. These are all animals that were pre-terrestrial, except Tiktaalik, which seems to be a weird hybrid. We've done some CAT scanning of some micro CT, I should say, of its pelvic area, and it's very clear that the bone thickness there is such that it was really doing something beyond just doing neutral buoyancy support. So it was doing something partially on land. But these were seemingly just Sarcopterygians leading up to land animals. And then we compare post-terrestrial, the first clearly post-terrestrial animals that we have in the fossil record. And you can immediately see that the eye orbit size is very clearly different, right, relative to the skull size, which is the important metric. So finally, how does this all relate to one type of consciousness, and how we might span evolved gaps in this type of consciousness with things like eco-feedback technologies? And that gets very, very speculative. But so here's one, I think, definition of access consciousness that I'm happy with. And again, this is definitely just access consciousness. I've become convinced by Merker's arguments that phenomenal consciousness is really important. It's the kind of consciousness that an animal in a fog would have. But I'm not trying to give an account of that. I'm only trying to give an account of this kind of consciousness, which is Bridgman quote is, consciousness is the operation of the plan executing mechanism, enabling behavior to be driven by plans rather than immediate environmental contingencies. So that seems to me like a lot of what's needed here once you get the ability to sense hundreds of body lengths in front of you. It's really a radically different situation. And there's all kinds of implications in terms of what kind of attentional mechanisms you might need, seeing so many things ahead of you, and so on and so forth. But and this gets to probably bringing the abject terror of my fellow collaborators to the fore. I think it's very interesting that if this is the ancestral condition in which we evolved access consciousness, and you can amplify your sensory volume by things like symbolic communication, for example, what bees do. They have a limited sensory range, although they have super good vision. But they dance to their conspecifics to get beyond that sensory volume. And we do the same thing. We have language. We have all kinds of things that gets us to escape this space. But the core of behavioral reactivity would be situated in the things that are immediately in our sensory volume, would be the idea. And so you think about, why is it that we have such difficulty with modifying behavior in regards to distant, either temporally distant or spatially distant effects, be it, reducing the amount of food we eat so that a year later we're a few pounds less, to, in particular, climate change, which is like a super big problem, right? And this is a really great paper called A Safe Operating Space for Humanity, where a bunch of geoscientists came up with 9 different categories or 9 different forms of habitability, dimensions of habitability for the planet, and sort of showed that, climate change, you might think we have a problem there, but spin the roulette wheel here, and biodiversity loss is, of course, a huge problem. And something I didn't realize till reading this paper is that the nitrogen cycle is also vastly out of whack. It's, to me, sort of an interesting thought that one of the things that might be going on is that we're failing to account for our need for feedback in the sensory volume. And so there's a bunch of people now working as a branch of human-computer interaction on something called eco-feedback technologies. This is a figure from one of the theses of one of those students, John Froelich, where he sort of says, look, we get food bills that look like this, and that lets us do things like, well, if we're spending too much on, coffee, we can sort of do something about it. But energy is given to us in this form: total food units, 1527, total price, 642. And so what these guys are doing is they're developing a whole bunch of really novel technologies that sort of give you immediate feedback as to how much energy you're using in all your appliances and so on and so forth. And it's very much the Prius cockpit model, right? So there are all these hypermilers now that they can see how many miles per gallon they're using in their immediate sensory space, they're modifying their behavior to reduce the amount of energy that they're consuming. And so I think this model is, somewhat interesting. But so how might we re-engineer access consciousness of Homo sapiens then? We could enhance awareness through technological artifacts such as Prius feedback, energy use feedback, and cultural artifacts. And what I mean by that is there's this thing in the U.S. called the Federal Toxics Release Inventory. And this is something mandated based on an opinion piece in 1982 in the New York Times, where the federal government now demands that all companies sort of publish their total number of pounds of emitted toxic substances. And I was told recently by somebody that DuPont, a DuPont VP, found a few years ago that they're in like the top 5 of that list. And so he immediately ran down to his people and said, we got to get off the top 10. This is unacceptable. It's just bad for PR, nothing else, rational self-interest here. And so there are things like that. That's, again, an example of feedback on a sort of a bigger time scale, bigger spatial scale. Amplification of working memory and other cognitive capacities central to long-term planning might be really helpful. And I'm glad to see I have a few more minutes where I can cover a couple of additional points. So the first point I'd like to cover is, did the ability to plan over large sensory volume come about as an adaptation of pre-existing neural machinery for spatial maps that are present in our fishy ancestors? So aquatic animals have spatial maps, just like have been demonstrated in rodents. And you can muck with them. If you ablate the dorsal lateral pallium of the fish, which is thought to be medial to, or homologous to medial pallium, which is thought to be homologous to hippocampus in mammals, you kill their ability to do spatial map navigation. So what's interesting about spatial maps is the following. In some sense, you're accessing a larger volume of space, right? But it's not a sensory space. It's a learned space. Where that's really effective is in things like foraging for food and other things where the targets of your behavior are non-dynamic, that they don't change over time, or at least over learning time, unlike, for example, the position of a prey, a mobile prey, which does change over real time. So it's great, right? For spatial maps, for non-dynamic things, you can work quite well with this large space. But it doesn't get you to manipulation of features to track a predator, or a prey, I should say, that's mobile. So I hypothesize something that's very interesting is that in rodents, it's been found now from Reddish's lab. This is a T-maze, and this is showing you the rat in the white circle and what its place cells are doing. And the place cells jump ahead to where it thinks it might go in the future. And so what may have occurred then is a tweak to the neural machinery so that we, instead of operating over spatial maps, which have this disadvantageous feature of not letting us cope with real-time change, we tweak it so that we can actually operate over sensory inflow. So this animal is actually looking down one side, looking down another, processing sensory inflow, and projecting itself into that future. So this is, I think, an interesting possibility that was what one of the tweaks that occurred in terms of neural implementation. So another point I'd like to mention is that people often say that animals have giant sensory spaces. Think of sharks; they can smell an injured animal from kilometers away, or animals can hear for hundreds of kilometers underwater. Very true, but not that important, because what that gets you is it gets you taxis. It gets you being driven towards, say, an odorant through following a gradient. But it doesn't get you envisioning trajectories through space. So do the following thought experiment. Just imagine you're really upset that you've had to learn so much about fish, and you're going to take action. So you're gonna come and attack me and take me down, and you're looking at various ways you might do it, like come along the side and sneak up behind me, or maybe take a door that's in the back there. You're thinking of various ways. Now, do the same process, but with a blindfold on, right? Now, clearly, if you mastered this environment with the blindfold previously, then that might not be such a problem. But I'm saying you don't have a spatial map, right? You're operating over sensory inflow. You need the resolution. You need an imaging sense. It doesn't matter that it's vision. Dolphins do it just fine with sonar. And in fact, sonar has attenuation lengths in water similar to light has in air. So that's a fascinating point about why certain very smart mammals have coped with the very unpleasant sensory environment of the water by taking high frequency sound production and hearing that evolved in mammals and producing an imaging sense with it. And finally, and so that actually tied in a little bit to this dolphins and whales point I was going to make. But also there's this issue of the octopus, which I have to say straight off that I don't have a completely satisfactory account for. One thing about octopus is that, like squid, they are under significant predation stress from the smartest animals in the water, which are dolphins and whales. So that's one point. Another point is that octopus, the Sarcopterygians seem to have been fish that move fairly rapidly and terrorize the smaller fish around them. Octopus, on the other hand, sort of hang around, look at a fairly complex scene and analyze it and attack it. So it looks like, maybe they actually had a need for doing some of the things that I'm referring to, although I'd argue that their sensory range is still a fraction of what the first animals onto land got to. And finally, octopus might have just come to, if they are in fact if they do in fact have some form of access consciousness, that they might have gotten to it in a very different way than the vertebrates did. And I'd be delighted if any part of this story as to how vertebrates might have come to access consciousness were true, let alone that it explains an invertebrate's trajectory. That's a divergence of 500 million years ago that they were last common ancestors. So I'll close now with a little upcoming work from my lab with Dave McLean. So I did a lot of work in the electric fish system, as I've shown you, But the electric fish system has a disadvantage in terms of not having the best of molecular and genetic techniques for crashing through circuitry with. So we have new work now where we've done an enormous amount of prey capture work. We've sort of redid the knife fish stuff, but now with vision and now with mocap data of zebrafish pursuing paramecia. That's something I didn't realize, but larval zebrafish, which are only fish that are 4 millimeters long, hunt paramecia, which are like 20 micron size single cell animals. And so I'm hoping that we can use a lot of the techniques that have been developed in larval zebrafish for crashing through circuitry for getting at first what happens in the midbrain, and then starting to see, they have a telencephalon with pallial structures, DL, for example, which seems to be where the spatial maps are, starting to get to those, although that might require an adult, we're not totally sure. But one of our initial findings is from all the prey capture work, we were able to predict where on the retina these animals make sure the prey lie after orientation and after swimming. And we can work back, where do those cells, those ganglion cells that get that information, where do they go in the tectum? So we've done that, and then we did something which we never thought would work. People have done microstimulation of the tectum before, and they've not seen enormously interesting things. So we targeted the region of the tectum where these signals relating to prey are thought to go based on our kinematic analysis and analysis of where the prey are. And we triggered, and unfortunately I don't have a movie to show you, we triggered prey capture motions. So this is really exciting to us, and we're hoping that this is going to lead to a whole bunch of really cool data soon as to how the tectum processes, and then we'll start getting to the maps and start to hopefully do some comparative analyses with ancestors, or descendants, I should say, of Sarcopterygians in terms of what's going on with the switch of neural circuitry. And with that, thank you very much.
Hi, Matt Carlin from University of Montreal. So